Hello, how are you? Joshua Lillian.
Fine, thank you, sir. You.
Yeah, a little bored, but I'm okay.
No, sir.
Lillian, I'm bored with you.
Oh, sir. What
The
did
reason
I
why,
do?
the reason why I said that, but since you laughed, I have to say it.
Sir, really?
Oh, yeah,
Sir, please, I'm sorry.
last week I was just sitting, I was thinking, Lillian. I can't, if I can't find Joshua Christ, okay, but Lillian. I was like,
Sir, it wasn't my fault.
I
So.
knew that, I know I'll get you.
I was just the network.
No, I know I'll get you, so.
Oh, sir, I'm sorry.
Oh, no. I'll get you. I mean, it's a matter of time. See myself. Why? Okay, so are you able to access the online e-learning platform? Are you able to access the e-learning platform?
Sir, please do me.
Are you able to access the e-learning platform?
Not really. Not
Why?
all
Because
of it. I'm able to log in.
you haven't paid your fees or something like that.
Yeah.
So in that case, then you can access it, right? Because I need to give you some assignments. I need to give you an assignment, and then I think maybe mid-semester is so close. It's closer than we think. So I give you a foretaste of the end of semester exam. So I think it's very important that you are all able to access, because if I want to give you an assignment, I can't even put it. Just loading on the WhatsApp platform, it's not the ideal thing. So try and connect to the e-learning platform. Is that okay? As soon as possible. All right, guys. So let's do something, and that is, take note of that. You need to be able to log on to the e-learning platform so that I can put my assignments in. It's very important.
Okay, sir.
All right. So let's continue from where we left off. I hope you are following what we're talking about. We actually talking about, the last time we talked about interior orientation. And interior orientation, we said, was to restore the geometry within the image space. Is okay. And the geometry of the image space is such that, we have a focal length. Okay, we have the focal length being a distance from the perspective center, to the lens, the center of the lens. So this distance here is actually F. We need to ensure that this type of geometry, is enforced. So 90 degrees to that, okay? And if we miss the vertical, then we have the nadir point. I think we've done all that before in photogrammetry 1. Okay, so this kind of geometry is what we are trying to, for example, at this point, we have the centering error. If there's anything like the centering error, centering the photograph such that the center of the photograph intersects with, the principal line. Are you okay? All right. So we need to do that. We say another name for the focal length is actually the principal distance, and the reason is because that line goes through the principal points. So setting the right type of principal distance is part of the interior orientation. Is that okay? So IO is what our focus has been on, interior orientation, and we've talked about a few things that could influence the geometry, that as we see it over here, because the photo coordinate system is a Cartesian one. Okay, it's a Cartesian one, and that means that the y and the x-axis are orthogonal. Are you okay? So if the x, that means the fly direction, and then it's 90 degrees to the y. Are you okay? And then we expect that the two axes will intersect at 90 degrees, etc. Anything that is making us not have this geometry is actually the reason why we do the interior orientation. Okay, so it's very important for you to understand that what we're talking about is nothing. In fact, photogrammetry 1 will be more difficult than photogrammetry 2. Are you okay? If you ask me, that's what I would say, because it's just the same basic principles being moved around. Are you okay? All right. So we touched on atmospheric refraction. We said that atmospheric refraction causes the light to move away or to deviate from the theoretical path. Are you okay? So if the light is supposed to go to say light travels in a straight line, children are singing it in a song. Are you okay? Meanwhile, adults are seeing something else, that the light is actually getting bent. Are you okay? All right, so we call that refraction. And so refraction then correcting for this error, which causes the image, that we are recording on the photograph not to be where they are supposed to be. Are you okay? So we think it's here, but then it's a little bit shifted. So then we have a certain error, which we are trying to, we could call it xi r or dr, doesn't matter mathematically. We're talking about the same things. Are you okay? All right, so that is interior orientation for you. Anything at all that causes the geometry within the image space to change, then we have to correct that, and that process is the interior orientation. We talked about F curvature, which also state that we assume that the ground or the object space is actually relatively flat. Not relatively flat, but it's actually projected on a plane. Are you okay? So we expect a geometry of this sort to exist, but really that's not what really happens. We have something like that. See, so the datum is not really this one, as the books are saying. It's more like that. Okay, so we need to find a way to actually correct this. And so because within the photograph we have a shift. This point here rather gets recorded, but we think it's actually coming from the other point. So then again we have a certain error, dr or del r. Are you okay? Right. So you can just do the same thing for other processes or other phenomenon. Are you okay? One of the interesting phenomenon that I wanted us to talk about last week and spend time on, which is becoming your assignment today, because that is your punishment, will be lens distortion. Next time you won't miss a lecture again. Is that okay? No, I'm not that weak. I'm very lovely. It's okay. Very lovely. I'm not mean. I'm very nice. But then I think sometimes teachers are always coming across as mean. I'm not. Lens distortion, it actually refers to the lens, the grinding of the lens. Are you okay? And the way the lens has been cut So we're talking about the curvature of the surface of the lens. Is all right. They are, in fact, all the distortions in lenses are called aberrations. Is okay. They are called aberrations. I like the word. I don't know why. Aberration. All right. So the aberration then means that we are having some kind of, it's a distortion. Are you with me? An imperfection of a sort. So you can have, astigmatism, coma. Are you okay? There are different types of lens distortion that you can have. And so there's a guy called Seidel who actually tried to classify, are you okay? So to write, the different types, are you okay, of aberrations that you can have, astigmatism, are you okay, etc. Then radial lens distortion, lens distortion, geometric. There is an aspect of aberration which is actually geometric, which is the last one that I'm actually talking about. Oops. What's going on here? Okay. Which is not coma, it's not astigmatism, it's not curvature of field, etc. All right, so let me actually refer to my notes. It's easier for me that way. Go back to it. All right. So we have different types, as Seidel listed them. Astigmatic, chromatic, aberration. That one is color. When light gets focused, based on the different, wavelength. Remember that light can be seen to be, a particle or as an energy, like we have those theories. But then in the case of chromatic aberration, then we have light being focused based on the frequency, because obviously visible light is made up of, red, blue, they are components of it, okay, green, etc. And the combination is what's giving us all the beautiful colors. So curvature of field is there. Then we have the distortion. So the attention should be on distortion. All right, so hold on, let me see if I can. Anytime I come into the PDF, then yes, so this one here, you can see my spotlight distortion. So we have so many of them. So the focus is on distortion. The whole idea is that one can be modeled and it's quite geometrical. Are you okay? So if a guy called Conradi came up with, a mathematical formula or relationship between the error caused by, as a result of the lens distortion, and then the radial distance, is that okay? So on the left hand side, we have the actual error, and then the right hand side we have, the so-called coefficients. Is that okay? So this is a polynomial in which we have coefficients to solve for, and then we have the r being the radial distance. Is that okay? That's the radial distance. All right. All right. So it's possible to then model, are you okay, what the error is based on where you are on the photograph. Are you okay? And we found out from the other formulas that were developed that the farther away that you are from the principal point, which is the center of the photograph, and the errors kind of tend to increase. Is that okay? Right. So yeah, so radial lens distortion is the topic that I actually intend to give it to you as an assignment, okay, because you didn't show up last week. So I have to let you pay a price, a little price. Is okay for not showing up. Okay, so this is how it works. When you look at this diagram, then you can see that we have the center of the photograph around this area, and then we have the light, the points being the image being captured, being displaced by there. I think it's not the first time we are seeing such a thing, but I think the nice thing about this diagram is that we're able to now show the components of del R. Okay. So the components of del R is that they're actually del X and then del Y. Is that okay? Pythagoras theorem will tell you that del R is equal to del R squared is equal to del X squared plus del Y squared. Okay. Hence you end up with something like this 90 degrees. Is that okay? So then you can do the Pythagoras theorem. So the hypotenuse is here, is this one. Okay, now we can write the same thing. R squared is also equal to S squared plus Y squared. I'm going to show you what I'm talking about. It follows. It's actually in the notes. So I'm just giving a teaser to it. Is that okay? Talking passionately about it, which is what the lecture is all about. Okay, so now R squared is equal to X squared plus Y squared is what I just talked about, and that is what you're looking at. All right, now here we are using similar triangles so that the distance along the hypotenuse shared by the two triangles. All right, so if I were to name this, which it's not going to be easy writing on this one, it's always funny the drawing with this one. So if this were A, this were B, this were C, D, E, then we can say that triangle ACD is similar to triangle ABE. Are you okay? So triangle A, I'm using my mouse to write, so it's going to look funny. ACD is actually similar to triangle ABE. All right, and as a result, we can now write those equations, this particular equation here. All right, this one. So the reason we can write is because we have similar triangles. End of story, nothing more. I think we've seen more complicated formulas than this. So by relating we can actually take 1/2 of the equation. We can take del R over R equal to del X over X, and then make del X the subject. Then we'll be finding the X component of the arrow. Are you okay? Etc. As we can see in this formulas that follow. Is that okay? All right. Now in this formula, we've actually factored out R, and then we are actually replacing it with, because Conrad actually found the del R. So del R here, if you factor del R out, you have X over R. Are you okay? And then the R now divides the actual R in the first equation up there. The first equation I showed you in this one. Okay, so we're doing a substitution right into that. And so we can now have these equations. Are you okay? All right. So then again, I think one of the things I always talk about in this class is for you to understand this part of the equation. Is okay. This is let me write it again so that you see it's actually XC subscript C. I can't write my subscripts very well, and I don't want to use capital X. That would be for the ground coordinates. Okay, so X minus del X. Okay, so let me tell you what is really happening here. You are actually correcting the X coordinate, so the X photo coordinate with the corrected by the arrow. Okay, as part of your interior orientation. This is the last topic under interior orientation, and we are correcting it by applying it. Are you okay? To it, and we get a corrected value of C. Is that okay? All right. So remember that the correction and the arrow are in opposite directions. Okay. So if I need to correct by del X, okay, then it means the arrow is actually minus del X. Please try to appreciate this. Is that okay? That if you need to, something is in error by a certain amount, if it's positive, then the correction has to be negative. Please put in your head, this is what the engineer needs to know. laborers, they don't care about this. Just tell them to cut it and they cut it. So listen and understand some of the wisdom behind some of the things you are looking at on the board, please. All right. I'm begging you. Okay. It's not like I'm belittling what you know. I know you know a lot, but pay attention and appreciate why some of the things are the way they are. Okay. So now the same thing is repeated for the x, the y. So y is equal to y minus del y. Are you okay? Right. So I think the example that we do is what makes it the whole thing kind of gel come to life. Okay. And we, like I said, we could do examples for the previous ones. So yeah, please take note of that. In this example, we take a camera calibration certificate, which I think we'll be using one. Not I think, I know we'll be using one, you know, as part of our tutorial with the ePhoto software. I told you to, you know, download it, the ePhoto software. So the camera calibration certificate gives you information about how the camera that was used, the parameters. Are you okay? In other words, what was the focal length of the lens that was in the camera, for example? So that is what the camera calibration certificate stand for. Are you okay? So I need you to actually go download the software, and then at the point we will actually use it, you will see that camera calibration certificate is normal. It's like it just goes with it. Is that okay? With your taking of the photographs. But when you take your phone and you take a photo of yourself, nobody really cares. Are you okay? You don't give people certificate for doing that. You just do it. You can just take your picture. But in photogrammetry, every photo that we take, every camera that is used, we need to have a camera calibration certificate. Okay, so guys, please go visit the website. Okay, download it. It's actually initially it was written in Portuguese. Is that okay? So you maybe find some Portuguese stuff in there. Go in there. If you are using a Linux machine, then you want to download the Ubuntu version. You're using Word, go for the 16-bit version, install it, because I can just give you marks for just installing it. Are you okay? I can just check on you guys anytime. It's very important. Download it. One of these days we are going to be using it, I'm sure, sooner than you think. It's all right, but we don't have time, honestly, guys. So yeah, going back to what we're talking about, the camera calibration certificate, that's what actually took us there. It's all right. It produces the data you're looking at on the board. It's all right. In other words, it's telling you that depending on where you are on the photograph, then you have a certain error. Are you okay? Yeah, you have a certain error, and these errors are actually in micrometers. Are you okay? So you have millimeters, micrometer, nanometer. So please go and pick your primary school exercise book and then refer, find out what it means to have micro. Are you okay? This microns, it's called microns, but it's actually like micrometer. Are you okay? All right. So that is 10 to the power minus 6 microns. That's what it means. Guys, I'm expecting you to know all this. And so please make the necessary referral. So 4 microns, 6 microns, 5 microns based on where you are. Are you okay? Based on where you are. So if you go back to what I was showing you earlier on, then you realize that we have the diagram at the very top where I put the F. Then the angles you're looking at, the field angle, is actually this one. Okay. So where I put the line, whatever image is there has this field angle, theta. Okay, and then we can have, the possibilities are many, that for millions of points on the photograph, we can have different theta's to it. basically that's the wisdom in what you are looking at. Are you okay? So I'm using the word wisdom. This week I've been watching a lot of videos on African countries and how their leaders were taught, but I think it's because JJ died. Not a very nice story, but anyway. Yeah. So basically, you can the certificate is also giving us decentering error, which we've talked about decentering, and I believe nobody asked a question, so you pretty much understand what it is. All right. So given the following values x, y, f, you're supposed to now determine the correction. Okay, how much should we correct for? All right. So the trick is to use interpolation, make a list of your distortion values, make a list of your field values. And then when you're done, simply find out what the radial distance is in this line. So the radial distance is actually r equal to f tan theta. Remember, we've discussed this. Okay, so r equal to f tan theta. Sorry, I can't write the symbol theta here. It's all right. So I've written theta itself. Okay. So f tan theta, then you can now ask yourself, what kind of angle do I have? Do I have it in degrees? Do I have it in radians? So when you look in the material I've given you, you see angle to rad and all that. It's just to scare you for nothing. Really, we're just taking the tangent of the angle, the theta that I showed you on the other side. Okay. So for the coordinates that we've been given and for the focal length given, are you okay? We can compute for all these values up here. Okay, we can compute the R. Okay, so everything you see here is actually the R's. All right, so these R's are the radial distances. These are all radial distances. Okay, being computed based on this value up here, these values. All right, okay, this is the distortion. Okay, so we don't want that, we don't need that. The angle is what we are talking about, the angles here. Okay, the angles help us to find this, plus the using the focal length and then the angle. So the angle is this one, and the focal length has been given up here. Okay, so we can compute so many R's, okay, so many radial distances for different field angles. Okay, so what is the field angle? Oops. Okay, when this lecture ends, please kindly use the same link. Okay, so you can see that clearly we've written field angle over here. So field angle. All right, and that is what we are actually talking about on the slide. The teachers that you are looking at, the red, yeah, this one. All right, great. So then what do we do from there? We're gonna do an interpolation. Okay, so you're gonna find, first calculate for R. How did we get this R? We get this R by simply doing R squared equal to S squared. Okay, I can go to the other board, but I hope you understand what I'm doing, right? I'm being a little lazy here. It's allowed. So square root of that. Okay. Will give us this R value. In other words, the X and then the Y have been given above over here. So you put them here, x goes there, square it, y goes there, square it, and then find the square root. You'll be getting the value here. So you try it, and if you don't get it right, come back for your money. Is that okay? You should be getting 36.351. Okay, now, so I'm being generous by putting this formula here because this is interpolation, and it's like a formula for doing interpolation. Is that all right? Okay, the 1000 is to simply take care of the micrometer to millimeter, because remember that our coordinates are in millimeters. Is that okay? Please, for your information, the coordinates are in millimeters. They can't be in any other thing than millimeters. Are you okay? They can only be in millimeters. It can be in micrometers. They can be in meters, because you can't have 30 meters on a photograph. So sometimes we have to, you know, like someone that I was working with said, he said, if you draw up a building, let it look like a building. At least if it looks like a building, it's okay. It's all right. Someone says radial distance. Think, what unit do you think that will be in? Well, of course, you should also be told. It's only fair. So we have, let me clear this. We have the 36.351 lying. Oh, come on. Lying in there, in between 20 and 40. Is that okay? And so if it lies in between 20 and 40, then we are simply going to do something that is interesting. We are going to say 4 goes with that, and then 6 goes with that. Is that okay? And if that is the situation, then what is the actual error in here somewhere? Are you okay? So there's an error in there between 4 and 6. So the value for the error for this point in question, 33.148, and then minus 14.92 up above here, is actually between 4 and 6. So we interpolate for it by just using proportion. Is that okay? I mean, so the good thing is that that formula has been given. Okay, you can try it. Okay, the 4 actually represents the value 4 that we are seeing up here, because we are increasing between 4 and 6. We are going up to 6. Okay, and then distort is the distortion value, the error, and then distance is the distance, the radial distance, etc. Is okay? So as an assignment, I want you to calculate and prove that the error is actually 0.0044. So go and work it out and show it to me. It's okay. I always remember that I give you an assignment. Don't forget that. It's okay. So go put it into this, or anyhow you understand interpolation. Interpolate between the two values, and then let me have the value. Now, once you have the error, it's a matter of putting it into this formula, which we've already, agreed that this formula is possible to use to have such a formula. And so you put it in, and then you have an answer. Okay. All right. So that is basic. This ends everything on interior orientation. If you have any question, you can ask. If you don't, I'll start talking about the next topic, which is relative orientation. And so I'm just giving a few seconds. Anybody who thinks like something is really not right, they can draw my attention to it, and then I'll look at it. Otherwise, I think you forever hold your peace. Is that okay? As they say, when two people are going to get married. Yeah. All right. Anyway, have you ever heard someone say that they have something to say at a wedding ceremony? You can also let us know. That would be interesting, isn't it? I won't allow him to marry her. Okay. But yeah. If you have anything, if something beats your mind, let me know. Except if you are washing your clothes whilst we are doing this lecture, yeah. And it's like, I don't care. You can't see me. One of these days, I'll ask that you put on your cameras. Is that okay? It's your orientation. Basically, that's that. We're done. We're going to talk about relative orientation. So let's get ready for that. It's okay. All right, someone is saying something, and I don't get what exactly that is. It's a symbol. I don't know what I said. Cockroach or what, I don't know. Okay, so now send them. I don't know, but I don't know what she means by that symbol. You can write so that I can get exactly what you mean. All right. So anyway, I'm sure she just laughing out loud. Let's look at relative orientation. Relative orientation is very easy to understand. Yeah. Okay. Okay. Of course. They always laughing. Ladies like laughing too much. I don't know why. Yeah. So relative orientation, I'll just talk about it because this Zoom meeting is going to end in 2 minutes, and then we'll use the other link. So I won't like talk a lot. I'll just talk about relative. The word relative is okay. The word relative means that, okay, so if I take two things, okay, my left hand, my right hand, okay, so relative to the two hands, okay, how far apart are we? Is determined by any of them. I can keep this close, and then we see they are close together. I'm bringing them together. So that is the idea of relative. The word relative. So relative orientation refers to the two photographs. Let's not forget that eventually we are interested in the overlap region. Okay, we are interested in overlapping photographs so that we can build what we call the stereoscopic neat model, which actually gives us the 3D data. Is that okay? Which is what we want. Is that okay? So flying over an area and taking pictures is nothing, it's not very interesting. What is interesting is if I can generate a 3D model of the area. So that is what relative orientation is all about. And then when we come back, we will look at it, more. We're going to look at what we call the one projector orientation, and then we have the two projector relative orientation. And the difference is that one of them we keep one. What are we actually moving them for? That's the question, isn't it? So the question is to actually form the model. Once you have interior orientation, the next thing is to form the model. So relative orientation means shifted. Are you okay? Bring this one, rotate it a little bit. So then we have to make use of the so-called omega phi kappa. Well, not so-called. I should be careful the use of the words, the phrase so-called. I think I just love it. But omega phi and then kappa comes in. Is all right. So I'm sure Louis is actually familiar with it. I'm expecting this meeting to end, and now Zoom is trying to be